Hello everyone, welcome to this video. In this video, we are going to learn about physics-informed neural networks using OpenMathAI. So, let's get started. What is PINN? Physics-informed neural network, PINN, is a supervised deep learning algorithm that combines neural networks with physical laws to solve both regression and scientific modeling problems. Unlike linear regression, decision trees, random forest, MLP, and traditional neural networks, which learn only from data, a PINN learns from both measured data and governing physical equations. It consists of an input layer, one or more hidden layers, and an output layer, while incorporating physical equations directly into the training process. This enables the model to produce predictions that are both accurate and physically consistent, even with limited training data. PINN starts by receiving the input variables and predicting the target output using a neural network. Instead of minimizing only the prediction error, it also checks whether the prediction satisfies the governing physical equations, boundary conditions, and initial conditions. The total loss is computed as a sum of the data loss and physics loss. During training, the network weights are updated using backpropagation and gradient descent until both losses are minimized. As a result, the model learns solutions that match the observed data while obeying the underlying laws of physics. Imagine we want to predict the pressure and velocity of water flowing through a pipeline. Instead of relying only on sensor measurements, the PINN also learns from the continuity equation and the momentum equation, together with the specified initial and boundary conditions. As training progresses, the model learns how pressure waves travel through the pipe, how velocity changes with position and time, and how these quantities satisfy the governing physical laws. This enables a PINN to accurately predict flow conditions even when no sensors are installed. We will use a true PINN transient pipe flow benchmark dataset for the PINN model. This dataset represents the transient flow of water through a 20-meter pipeline. Unlike a conventional machine learning dataset, it includes 600 sparse sensor observations, 12,000 physics collocation points, 201 initial condition points, 402 boundary condition points, and a 10,201-point reference solution for evaluation. The PINN uses position, m, and time, s, as inputs and predicts pressure, pa, and velocity, meter per second. During training, it combines the sensor data with the governing continuity and momentum equations while enforcing the initial and boundary conditions. This enables a model to accurately reconstruct the pressure and velocity throughout the pipeline, even in regions without sensor measurements. So, let's get started. OpenMathAI. In this demonstration, we use the pipe flow prediction using PINN model. Click Create New Project. Enter the project name as Pipe Flow Prediction. Choose a folder location to save the project, then click Save. To import your dataset, either click Load Example Dataset or browse for Dataset to import your own CSV file. Once the dataset is loaded, verify that it contains all columns before proceeding to model training. Scroll down to view the first 10 rows of sample data. Click Continue to Configuration to proceed. Configure the dataset by specifying the input features and output target. There's also a feature called Ignore, which can be used for columns that should not participate in model training. Select the input and output columns manually, or use Smart Suggest for automatic recommendations. There is one more feature, Signal Diagnostics. There's 3 columns. First one is column. It tells which features are in the dataset like inputs and outputs name. Second one is VI if it tells how much correlation the features. Third column is status if it's okay, moderate, high, redundant, and constant. Review the selected configuration. Click Proceed to Model Design. Choose a model from the available machine learning models. OpenMathAI recommends suitable models and features based on the dataset. For this demonstration, select the PINN model. View the model overview, pros, cons, and real-world applications. Click Proceed to Training. You will see the selected model. Click Start Train Models. Review the training configuration. Test data split, which determines a percentage of data reserved for testing and validation. Review the model parameters and pre-processing settings. Review the physics, PINN, settings. The software provides 4 PINN modes: equation specification, constraint-based physics, disabled, standard neural network, and equation discovery. If the governing physics equation is already known, select equation specification and enter the differential equation manually. If only the physical constraints are known, such as bounds, monotonicity, energy conservation, or stability, choose constraint-based physics and enable the required constraints. If you want to train a standard neural network without applying any physics constraints, select disabled, standard NN. For this example, select equation discovery. Review the system type options. The available system types include auto detect, ship speed control, battery management, thermodynamics, motor control, and custom. For this example, keep the system type set to auto detect. Keep the mode as auto discovery and the system type as auto detect. Review the collocation loss settings, including the number of collocation points, sampling strategy, and physics loss weight. Then click Discover Equation to automatically identify the governing equation from the training data. Once the equation is generated, review the discovered equation together with its R-squared value and confidence. If the discovered equation is satisfactory, click Accept Use in Training. And also another feature is added as Train from Scratch or Continue from Use model. If you train this model before you use that option, modify the configuration if required. Click Start Training to begin the training process. After training is complete, review the following performance metrics. R-squared measures how well the model explains a variation in the output data. Range 0 to 1. MSE, mean squared error, measures the average squared difference between actual and predicted values. RMSE, root mean squared error, the square root of MSE. RMSE is expressed in the same units as the output variable, making it easier to interpret. Engine time, the time required for the generated model engine to execute and produce predictions. Lower engine time indicates faster model execution, which is important for embedded systems and real-time applications. Fit quality, an overall assessment of how well the model fits the dataset. It is generally derived from metrics such as R-squared, RMSE, and residual errors. Model accuracy. For regression models, accuracy is commonly estimated using the R-squared value. Example, R-squared equals 0.95, accuracy almost equal to 95%. Click Fit to Window. You will see 3 types. Fit to Window, comfortable, compact. Then the clear history. If you click, then it will clear the history before its trained model. Another is deselect and select all trained models for export. Click View Curves to visualize the actual and predicted graphs for both pressure and velocity. Click View Math Code, mathematical model and code generated by OpenMathAI. The preview displays the LSTM architecture, the corresponding source code, and a detailed explanation of how the network processes sequential data. Open the Math view to visualize the complete PINN model architecture created from your training data. Maximize the Math view window to examine the flow of data from the input layer through the hidden layers and finally to the output layer. The architecture illustrates how the input features, position, and time are transformed through multiple hidden layers to learn the underlying physical relationship. The network predicts the target variables, pressure and velocity, while learning the governing behavior of the pipe fluid flow system. Once training is complete, OpenMathAI uses a learned network weights together with a discovered physical relationship to predict pressure and velocity for new position and time inputs without retraining the model. Return to the result page and click Deploy Status. Click Export Model. Choose the required export format: ANSYS, FMU 2.0, FMU 3.0, Verilog RTL, VHDL RTL, Python Bundle, ONNX Hub. You can choose any of these format and export. You can also download the free trial versions of OpenMathAI and Twin Simulate. Thank you. Stay tuned for more OpenMathAI demonstration.